let's consider for a moment the graph of a quadratic. I'm going to take it off the axis, but let's just assume we're in the first quadrant. And the graph of some quadratic function looks something like this. Right? And we'll say that we're going from point A to point B on the x-axis. So it's irrespective. Now, you know that you could find the slope from point A to point B, right? And so this is the slope of some secant line, right? And its slope would be f of B minus f of A, right? The two y values over B minus A, the two x values. Right? Now you can also see in this picture, I'll do this part in blue, that this curve, our original curve, has a variety of tangents, right? There'd be a tangent here, there'd be another tangent here, and they would have different slopes. But hopefully you can see even this, that there will be a tangent here at some point. It looks something like that, and it will be parallel to our secant. Or the slope of the tangent will be the same as the slope of the secant. At least one place in there. So we can see graphically that this must be true, that the slope of our secant line must equal the value of the derivative at some point. Maybe more than one point, but we can see that there is some point C where that's going to happen. Right? And notice that this is the slope of the secant. It's also the average rate of change. The derivative is the instantaneous rate of change. And there's some point on this interval where they will be equal. Now the average rate of change is also called the mean, average and mean being synonymous. And so this is an example of what's called the mean value theorem. Right? So mean is average, and it reminds me of average rate of change. And the mean value theorem is that for a function that is continuous, right? So these are conditions. The function must be continuous. On a closed interval. Right? And we need the closed interval because it's from the endpoints that we'll get our slope of the secant line. And differentiable. Right? It can't have a vertical tangent somewhere, for example. Right? So the mean value theorem wouldn't hold for an absolute value graph. Right? If that's true, then at least one place in the interval f prime of c must equal f of b minus f of a all over b minus a. Or the slope of the tangent line, f prime of c, must equal the slope of the secant line, the slope from endpoint to endpoint. Right? You must know the mean value theorem. Right? Know what it says and practice a lot of problems with it. It's pretty much guaranteed you'll see something that's referencing that, and you just need to know what the mean value theorem says. For me, the easiest thing to help remember it was mean and average, right? If a function is continuous and differentiable on a closed interval, the average rate of change must equal the instantaneous rate of change at least once. And it could be more, right? Because we could have a graph that looks something like, we start here, looks something like this. Here's my secant line, and it has a tangent. And I could have a derivative down here that's parallel, another one up here that's parallel, another one down here that's parallel. The mean value theorem guarantees that at least once that must happen on some closed interval.